All right, get ready to dive deep into the fascinating world of metal alloys. I have to say, you've given us quite a challenge with this textbook chapter.
Chapter 11, to be exact.
Yeah, chapter 11. It is dense, packed with tables and diagrams, and honestly enough metallurgical jargon to make anyone's head spin.
But fear not, we're here to break it all down for you. We'll distill the key takeaways, explain the concepts in plain English, and explore the real-world applications of all these metal marvels.
So, should we jump right in? The chapter kicks off with ferrous alloys.
The iron family.
Yeah, specifically iron and its many personalities.
That's a great way to put it, because even though iron is the base, it's the alloying elements that really give each steel its unique character.
Right, like adding different spices to a dish, you can get a whole spectrum of flavors, or in this case, properties.
Precisely. And the chapter dives right into the different types of steel. We've got your plain carbon steels, which are like the all-around workhorses.
Reliable, dependable.
Exactly. Then you have the high-strength, low-alloy steels, sometimes called HSLA steels. They're like the athletes of the steel world.
Strong and flexible.
Exactly. Packing a punch in terms of strength, but still maintaining good ductility.
It's like comparing a regular bike to a mountain bike. Both bikes, but one is built for tougher conditions.
A great analogy. And speaking of tough, the chapter also covers those often misunderstood cast iron.
Ah, yes, cast iron. People often think of it as being brittle and weak, but there's so much more to it.
Right, it all comes down to the microstructure. You see, gray iron, for example, has these flake-like graphite particles.
Like little flakes of, pencil lead?
Yeah, kind of. And these flakes actually make gray iron great at absorbing vibrations. That's why you often find it in things like engine blocks.
So it's like a built-in shock absorber.
Precisely. Then you have ductile iron, which has these spherical graphite particles. This small change in shape makes a huge difference in the material's strength and flexibility.
Really, just changing the shape of those particles.
You bet. Ductile iron is almost as strong as steel and can be used to make all sorts of things, like gears, crankshafts, even pipes.
It's amazing how these subtle tweaks at the microscopic level can completely change a material's properties.
The chapter also talks about some other, more specialized types of cast iron, like white cast iron, which is extremely hard but very brittle.
Right, white cast iron. It's so hard it can't be machined, but it's often used for wear-resistant applications, like liners for grinding mills,
And then there's malleable iron,
which, as the name suggests, is more malleable.
meaning you can shape it more easily.
Exactly. Malleable iron is often used for complex shapes that need good ductility, like pipe fittings in agricultural equipment.
And we can't forget about compacted graphite iron, or CGI.
The new kid on the block. It has a microstructure that's somewhere between gray iron and ductile iron, giving it a unique combination of strength, toughness, and thermal conductivity.
So it sounds like there's a whole spectrum of cast irons, each with its own strengths and weaknesses. Absolutely. And understanding those differences, particularly at the microstructural level, is key to selecting the right material for the job.
It's all about choosing the right tool for the job. But the chapter doesn't stop there. It ventures beyond the realm of iron and delves into non-ferrous alloys.
This is where things get even more diverse.
Hmm.
We encounter metals like copper, aluminum, magnesium, titanium, each with its own fascinating set of properties and a whole range of applications.
A whole new world of possibilities, and the chapter jumps right into copper and its alloys, starting with two of the most well-known, brass and bronze.
Ah, the classics, used for centuries and for good reason.
They're beautiful, they're corrosion resistant, they're great conductors of electricity.
Exactly. And while people often get brass and bronze confused, the chapter makes the distinction clear.
The key difference lies in the main alloying element, right?
Precisely. Brass is primarily an alloy of copper and zinc.
While bronze is typically copper and tin.
Right. Think musical instruments for brass and ancient statues for bronze. That's one way to remember the difference.
I like it. And the chapter also emphasizes how, even within these categories, there's a ton of variation. Different types of brass and bronze are used for all sorts of things, depending on their specific properties.
For instance, you'd want a different type of brass for a trumpet than you would for a doorknob. And certain copper alloys, like beryllium copper, can even be heat-treated to increase their strength.
Opening up a whole new range of applications. And that's a perfect segue to our next section. Aluminum and its alloys.
A true lightweight champion.
Known for being lightweight, corrosion resistant.
And very versatile.
Perfect for airplanes, beverage cans, and everything in between. The chapter explains how aluminum alloys are often given these temper designations.
Like T6?
Right, these codes that tell you what kind of heat treatments they've undergone.
Because those heat treatments can dramatically affect the alloy strength and other properties?
It's like a secret code that reveals the aluminum's hidden potential. And speaking of hidden potential, the chapter also touches on these fascinating aluminum-lithium alloys.
These alloys are becoming increasingly popular in the aerospace industry.
Because they're incredibly lightweight, but still incredibly strong.
Exactly. Ideal for aircraft structures where every ounce counts.
It all comes down to that concept of specific strength.
Right.
A measure of a material's strength relative to its weight.
Precisely. Aluminum lithium alloys have a very high specific strength, meaning they can carry a lot of load for their weight. It's a game changer for designing more fuel-efficient aircraft.
So aluminum is clearly a versatile metal with a lot to offer. But what about magnesium? It's often touted as being the lightest structural metal.
That's right, a true featherweight. The chapter dives into magnesium and its alloys, highlighting how they're being used in everything from aircraft components to luggage to even car parts.
It's amazing to see how far this metal has come. But it does have some challenges, right?
Well, it's not as strong as some other metals, and it can be susceptible to corrosion in certain environments.
So it's a bit of a diva, but with the right alloying elements and surface treatments, you can overcome those challenges and unlock magnesium's full potential.
Absolutely. And it's worth mentioning that magnesium has a rather unique crystal structure, a hexagonal close-packed structure, which makes it relatively brittle at room temperature.
So it's not something you'd want to bend or shape when it's cold?
Not without some careful consideration, no. But heating magnesium up makes it much more ductile, easier to work with. So you usually see it being cast or hot worked rather than cold worked.
Like how glass becomes more pliable when you heat it up. It all comes down to how the atoms are arranged within the material. But let's move on now to another lightweight champion, titanium.
A relative newcomer to the world of engineering materials, but it's quickly gained a reputation for being incredibly strong and resistant to corrosion.
And biocompatible. The chapter highlights how titanium is practically immune to the body's defenses, making it the go-to material for medical implants.
Hip replacements, dental implants.
It's amazing. And because it's so resistant to corrosion, even in harsh environments like seawater, it's widely used in marine applications as well.
You see titanium in everything from ships and submarines to desalination plants.
So it's strong, corrosion-resistant, biocompatible. It sounds like the perfect metal. But there's got to be a catch, right?
Well, the main drawback is its cost. Titanium is a reactive metal, which makes it challenging and expensive to produce.
So it's like the luxury sports car of the metal world. High performance comes at a price.
A good analogy. But for certain applications where lightweight, strength, and corrosion resistance are absolutely critical, titanium is often the only option.
Things like spacecraft, jet engines, high-performance bicycles.
Exactly. And now prepare yourself because we're about to enter the realm of the truly extreme refractory metals.
The superheroes of the high-temperature world.
We're talking niobium, molybdenum, tungsten, tantalum, metals that can withstand temperatures that would melt most other materials.
It's mind-blowing to think about these metals just chilling in extreme environments, like rocket engines and nuclear reactors, where most others would simply vaporize.
They're the real deal. And the chapter mentions that these refractory metals are often incorporated into superalloys.
Ah, superalloys. Those are like the rock stars of the metallurgical world, right?
Precisely. Designed to withstand incredibly high temperatures and pressures, essential for things like jet engines and gas turbines.
So it's like taking the already impressive properties of refractory metals and then boosting them to a whole new level. Makes you wonder, is there a limit to how strong and heat-resistant we can make these alloys?
That's a great question, and one that materials scientists are constantly exploring. But before we get carried away with these super strong materials, let's not forget about the classics. Noble metals.
Ah, yes, gold, silver, platinum, always a crowd pleaser. The chapter highlights their beauty, their resistance to oxidation, which is why they're so highly prized in jewelry.
But they're not just about sparkle and shine.
Right, they have important industrial applications too.
Platinum, for example, is a crucial catalyst in many industrial processes, including the production of gasoline. And gold, with its excellent electrical conductivity and resistance to corrosion, is widely used in electronics.
So even though they might seem a bit flashy, noble metals play essential roles in many aspects of our lives.
They really do. And the chapter rounds out this section with a quick look at some other, shall we say, more utilitarian metals like nickel, lead, tin, zinc, and zirconium.
Each one with its own unique set of properties and uses.
It truly is a diverse world out there when it comes to metals. And before we move on to the next section, I wanted to highlight a fascinating case study. The chapter mentions the metal alloys used in euro coins.
Oh yeah, I remember that. What was so special about them?
Well, it's a great example of how material selection isn't just about finding the strongest or most heat-resistant metal. You have to consider a whole bunch of factors, like cost, durability, security, and even aesthetics.
Right, it's got to look good too.
Exactly. And in the case of the euro coins, each denomination has a specific alloy composition that gives it a distinct color, weight, and even electromagnetic signature.
So they're carefully engineered to be both functional and, well, beautiful.
Precisely. It really highlights how material science isn't just about theoretical properties, it's about solving real-world problems and finding the best materials for specific purposes.
And with that, I think we're ready to move on to the next stage of our journey. Shaping metal.
From molten mass to finished form, get ready to explore the amazing processes that transform raw metal into useful objects. So we've talked about all these amazing metals and their unique properties, but how do we actually shape them into useful objects? That's where forming operations come in.
Right, it's like having a pantry full of delicious ingredients, but you need the right tools and techniques to turn those ingredients into an amazing meal.
I like that analogy. And the chapter starts by discussing two fundamental approaches to shaping metal: hot working and cold working.
Hot working, that sounds pretty self-explanatory, right? You're working with the metal while it's hot.
Yeah, exactly. Imagine a blacksmith hammering a piece of red-hot iron. That's hot working in action. You're deforming the metal at a high enough temperature that it can recrystallize as it cools.
Recrystallize, so the internal structure of the metal basically rearranges itself.
Precisely. And this keeps the metal soft and ductile, allowing for large deformations without cracking.
But I imagine it also means you don't get the most precise shapes.
That's right. Hot working is great for shaping large pieces of metal, but it typically results in a rougher surface finish.
So it's like molding clay. You can really push and pull it into different shapes when it's warm. But what about cold working?
Think of bending a paperclip. You're deforming the metal below its recrystallization temperature, which means it's going to push back a bit more.
And probably get stronger in the process,
Yeah,
right?
exactly. Cold working makes the metal stronger and harder, but also less ductile. It's great for achieving precise shapes and smooth surfaces, but it can lead to cracking if you push the metal too far.
It's like trying to bend a cold piece of spaghetti. Too much force and it'll snap. So the chapter goes on to describe the four main forming operations: forging, rolling, extrusion, and drawing. And each one has its own unique way of shaping metal.
Forging, for example, is like sculpting with a hammer, but on a much larger scale.
It's the classic image of a blacksmith shaping a horseshoe, right?
Precisely. Forging involves shaping metal by applying compressive forces either through repeated blows or continuous squeezing.
And I remember the chapter mentioning that forging can be done in two main ways: closed-die forging and open-die forging.
You've got a good memory. Imagine you have a cookie cutter. In closed-die forging, the metal is squeezed between two dies that have the desired shape, much like pressing cookie dough into a mold.
So it's very precise.
Extremely. Closed-die forging creates parts with very tight tolerances and little wasted material. Open-die forging, on the other hand, is more like shaping dough with your hands. You use simpler dies that don't completely enclose the workpiece, allowing for more flexibility in the shapes you can create.
So closed-die forging is perfect for mass production of identical parts, while open-die forging allows for more custom designs.
A great summary. And it's worth noting that forged parts are known for their strength and toughness.
Why is that?
When you forge a metal, you're essentially aligning the grain structure, making it more resistant to cracking and fatigue. That's why forged parts are often used in critical applications like crankshafts, connecting rods, and turbine blades.
This is like how twisting a bunch of fibers together makes a rope stronger. The chapter then moves on to rolling, which is like the industrial scale equivalent of flattening dough with a rolling pin.
Exactly. Rolling involves passing metal between two rollers to reduce its thickness, producing sheet, plate, or even foil.
It's amazing how thin they can roll some metals. I'm always impressed by how thin aluminum foil is.
It really is remarkable. And rolling, like forging, can be done hot or cold depending on the desired properties.
So you can fine-tune the material's properties based on how you roll it.
Precisely. And the applications of rolling are vast, from car body panels and aluminum foil to I-beams for bridges and buildings.
It's clearly a workhorse in the metal forming world. Next up, we have extrusion, which is a bit harder to visualize. The chapter describes it as squeezing toothpaste out of a tube, but with metal.
A good analogy. You're essentially pushing metal through a die to create long, continuous shapes with a uniform cross-section.
So you can create really complex shapes this way.
Absolutely. Everything from simple rods and tubes to intricate profiles with all sorts of twists and turns.
And it's not just limited to certain types of metal, right?
Nope. Extrusion can be used with a variety of metals, including aluminum, copper, and even steel, though extruding steel requires significantly more force.
Finally, we have drawing, which the chapter describes as pulling a wire through a progressively smaller hole.
Exactly. It's used to reduce the diameter of wire or rod or to create seamless tubes.
It's incredible to think about how they make those super thin wires used in electronics.
It's a very precise process that requires careful control of the drawing force and lubrication.
But now let's shift gears and talk about casting, which is a completely different way of shaping metal. This is where we get to play with molten metal.
It's like the ultimate baking experience. The chapter starts off by talking about sand casting, which is the most common casting method.
Sand casting, so you're literally making molds out of sand.
Exactly. It's a relatively simple and inexpensive process, which is probably why it's so widely used.
You can create all sorts of parts with sand casting, right?
Oh, absolutely. Everything from engine blocks to manhole covers to intricate sculptures.
It's amazing what you can do with sand and molten metal. But what about when you need more precise shapes? The chapter mentions die casting for those applications.
Right. Die casting is like the high-precision cousin of sand casting. It uses a reusable metal mold to create high-volume, intricate parts with excellent dimensional accuracy.
So it's perfect for mass production.
Exactly. Think of all those tiny gears inside a watch or the complex housings for electronic devices. Those are often made with die casting.
But die casting is typically limited to metals with low melting points, right?
That's right. Aluminum, zinc, and magnesium are common choices for die casting.
So what about those really intricate parts that require extreme precision and maybe even involve metals with higher melting points, like the turbine blades in a jet engine? The chapter mentions investment casting for those, right?
You're on fire today. Investment casting, also known as lost wax casting, is a fascinating process. Imagine creating a metal sculpture from a wax model.
So you create a wax pattern, make a mold around it, melt the wax out, and then pour molten metal into the resulting cavity.
You've got it. And the result is an incredibly detailed metal part with excellent surface finishes.
It sounds like a magic trick. The wax disappears, and you're left with this intricate metal part.
It's a remarkable process, and the chapter also mentions a variation of investment casting called lost foam casting, which uses a foam pattern instead of wax.
Ah, so the foam evaporates when the molten metal is poured in.
Precisely. It's a newer technique that's rapidly gaining popularity, particularly in the automotive industry.
And we can't forget about continuous casting, which the chapter describes as a process for creating large, continuous sections of metal, like billets and slabs.
Right. Continuous casting is a key process in the production of steel and other metals. It's like a metal factory that never stops running.
It's incredible to think about those massive slabs of steel being produced nonstop. But now let's move on to one of the most fascinating aspects of metalworking.
Heat treatment.
This is where we unlock the hidden potential of metals. By carefully controlling the temperature, we can actually change the internal structure of a metal, altering its properties in remarkable ways.
Okay, so we've talked about how to mold and shape metal, but the chapter doesn't stop there. It dives into this fascinating world of heat treatment, where we can actually change the internal structure of metal just by playing with its temperature.
It's like having a secret code that unlocks a whole new level of strength, flexibility, and even wear resistance. It's amazing to think that we can manipulate a metal's properties just by controlling how hot or cold it gets.
And it all starts with understanding a process called annealing.
Annealing, that sounds very zen. Is it like giving the metal a spa day?
In a way, yes. Annealing involves heating a metal to a specific temperature and then slowly cooling it down, relieving all the internal stresses and making it softer and more ductile.
So it's like taking a tangled mess of yarn and gently combing it out until it's smooth and even.
Exactly. Annealing can also refine the grain structure, making it more uniform and less prone to cracking. And the chapter mentions that there are several types of annealing, each with its own specific purpose.
Right, like process annealing, which is used to soften cold-worked metal and make it easier to work with.
And stress relief annealing, which is like giving the metal a massage to get rid of any residual stresses that might have built up during manufacturing.
And for ferrous alloys, specifically steels, there's normalizing, which helps refine the grain structure and improve the machinability and toughness of the steel.
Exactly. It's all about tailoring the heat treatment to achieve the desired properties.
So we can soften the metal with annealing, but the chapter also talks about hardening, which sounds like the opposite.
That's right. Hardening is all about making the metal stronger and more wear-resistant. And for steels, the key to hardening is a process called quenching.
Quenching, so you're rapidly cooling the steel from a high temperature.
Precisely. And this traps the atoms in a very hard but brittle structure called martensite.
So it's like suddenly freezing a fast-moving river. The water molecules get locked into this rigid, crystalline structure.
A great analogy. But as you might imagine, hardened steel can be a bit too brittle for some applications. That's where tempering comes in.
Tempering, so you're reheating the hardened steel to make it less brittle.
Exactly. Tempering allows us to fine-tune the balance between hardness and toughness, making the steel less prone to shattering while still retaining as much strength as possible.
It's like taking that frozen river and letting it thaw just a little bit so it becomes more flexible. And the chapter also introduces this concept called hardenability, which sounds a bit intimidating.
Hardenability is simply a measure of how deeply a steel can be hardened by quenching.
So some steels harden easily throughout their thickness, while others only harden near the surface.
Precisely. And to measure this, we use a clever test called the Jominy end quench test.
The Jominy end quench test, how does that work?
Imagine taking a red-hot steel bar and spraying one end with a jet of cold water. This creates a range of cooling rates along the bar, resulting in different microstructures and hardness values at different distances from the quenched end.
And by measuring those hardness values, you can determine the steel's hardenability.
Exactly. It's a really useful test for predicting how a steel will respond to heat treatment. And the chapter also points out that certain alloying elements, like chromium, nickel, and molybdenum, can significantly increase the steel's hardenability.
So we can tweak the recipe to make the steel even harder. But let's move on now to another intriguing heat treatment process: precipitation hardening.
Precipitation hardening. This is where things get really interesting.
It sounds a bit like something out of a chemistry lab. What exactly is precipitation hardening?
It's a technique we use to strengthen certain alloys by forming tiny particles of a second phase within the primary phase matrix. These particles act as obstacles, making it harder for the material to deform.
So it's like adding sprinkles to ice cream. Those sprinkles make it harder for the ice cream to melt.
A delicious analogy. And the formation of these strengthening particles involves a two-step heat treatment process. First, we do a solution heat treatment, where we heat the alloy to dissolve the second phase completely. Then we quickly cool it down, trapping the second phase in solution.
So it's like dissolving sugar in hot water.
Precisely. The second step is precipitation heat treatment, where we reheat the alloy to a lower temperature, causing the second phase to precipitate out of solution in the form of fine particles.
It's like making rock candy. You dissolve sugar in hot water and then let it slowly cool, allowing sugar crystals to precipitate out.
Exactly. But instead of sweet treats, we're creating stronger metals. And just like with tempering, the time and temperature of the precipitation heat treatment can be carefully controlled to fine-tune the size and distribution of those particles, ultimately determining the alloy's final properties.
So it's all about finding that sweet spot, the perfect balance of time and temperature.
Precisely. And the chapter even mentions that some aluminum alloys can undergo natural aging at room temperature, meaning the precipitation hardening happens over time without any additional heat treatment.
So the metal is slowly strengthening itself over time, almost like it's alive.
In a way, it is, but for most alloys, we use artificial aging, which involves heating the alloy to a specific temperature for a controlled amount of time to achieve the desired properties.
And the chapter also mentions that precipitation hardening can be combined with strain hardening, which we talked about earlier, to create even stronger alloys.
That's right. By combining these two techniques, we can push the strength of certain alloys to remarkable levels.
But there's a limit, right? The chapter mentions something about overaging.
Yes. Overaging is what happens when you expose the alloy to too much heat for too long, causing the precipitated particles to grow too large and actually weaken the alloy.
So it's like leaving the rock candy solution in the fridge for too long. The crystals grow too big and the candy becomes grainy.
Exactly. It's all about finding that sweet spot, that Goldilocks zone, to achieve the optimal balance of properties.
But the chapter doesn't just focus on heat treatment. It also introduces this intriguing process called powder metallurgy.
Powder metallurgy is like baking a cake, but instead of flour and sugar, you're using metal powders. You press these powders into a mold and then heat them to a high temperature, causing the particles to bond together and form a solid object.
So it's like making a metal sculpture out of tiny grains of sand.
A good way to think about it. And one of the advantages of powder metallurgy is that you can create parts with very precise shapes and compositions.
You can even make parts from metals with extremely high melting points, which would be difficult or impossible to cast.
Exactly. And the chapter even mentions that you can create porous metal parts using powder metallurgy.
Porous metal parts, so they're like tiny sponges made of metal.
Precisely. And these porous metals are used in all sorts of applications, from filters that can trap contaminants to bearings that can hold lubricant.
It's amazing how versatile these metal powders can be. And speaking of joining metal parts together, the chapter concludes with a section on welding, a process that's essential in countless industries.
Welding is like the glue that holds our modern world together, allowing us to join different pieces of metal into larger, more complex structures.
And the chapter emphasizes the importance of choosing the right welding process, the right filler metal, and carefully controlling the cooling rate to avoid any defects.
It's a complex process, but when done correctly, welding can create incredibly strong and durable joints.
Wow, we've covered a lot of ground in this chapter, from the diverse world of metal alloys to the intricate processes used to shape and treat them. It's been an incredible journey.
And it really highlights the incredible ingenuity and creativity of materials scientists and engineers who are constantly pushing the boundaries of what's possible with metals.
It makes you wonder what incredible new alloys and processing techniques we'll see in the future.
Who knows? Maybe we'll have self-healing metals or alloys that are lighter than air. The possibilities are truly endless.
So there you have it, folks, a deep dive into the amazing world of metal alloys. We hope you've enjoyed the journey and learned something new along the way.
We encourage you to keep exploring and keep asking questions about the materials that shape our world, because understanding how materials work is essential for building a better, more sustainable future.